All right, good morning, guys. Welcome to my streamlined discussion of bond energy. So I'm going to try to keep this under 3 minutes. Ready, set, let's go. Okay, we briefly discussed lattice energy, and lattice energy would also be synonymous with lattice strength. But when we're talking about lattice stuff, we're talking about ionic compounds, which we know are metal and nonmetal. So we're talking about the energy it would take essentially to pull the ions apart from each other. When we're talking about bond energy, we're also talking about bond strength. How strong the bond is. If it has a high energy, it's very strong. And this is for covalent compounds. And that's nonmetals. So when we talked about lattice energy, we said, okay, an increase in size led to a decrease in energy, and an increase in charge led to an increase in energy. When we're talking about covalent compounds, we're not talking about charge anymore, although you can look at electronegativity and it works very similarly, where the bigger the difference in electronegativity, the stronger the bond is going to be. But let's go ahead and look at it in terms of size to start with. So let's say we have an HF bond, an HCl bond, and an HBr bond. And we say, which one's stronger? In other words, which has the highest energy? Highest bond energy. That is the amount of energy it would take to pull these two apart. Well, just like with lattice energy, if you have an increase in size, you're going to have a decrease in energy. So if we look at these guys, as we go down and to the left of the periodic table, so we're looking at fluorine, chlorine, and bromine here. As we go down to the left of the periodic table, the size is going to increase. So therefore, bromine is much bigger than fluorine. So let's go over here. And if we were to draw it out, we'd say, okay, fluorine is this little dude, chlorine is getting bigger, and bromine is like that. And when we're comparing the distance between them, hydrogen would be the same, and hydrogen is not drawn in any way, shape, or form the way it should be. It should be very, very small comparatively. But when we're looking at the distance between them, we're looking at the distance between the centers, you can see pretty quickly that the distance between these two is much smaller. And the distance between these two is bigger. So just like people holding hand in hand, these two are closer together. These guys can like link arms. And these guys are barely holding fingertips. Which one's more difficult to pull apart? Well, obviously the linked arms. Therefore, these ones would be the strongest. So this bond right here, an HF bond, is stronger than an HBr bond. Another thing to think about when we're looking at bond energies is whether it's a double, single, or triple bond. The distance between these, as you add more bonds, they get closer together. So this would be smallest distance apart. In other words, these guys are closer together. If these guys are closer together, it's going to take a lot more energy to pull them apart. Therefore, these guys have the greatest bond energy. And they're the strongest. So if they're close together, close equals strong. Whereas these guys are just farther apart. It's a single bond, they're farther apart. This would be the weakest. Weakest because they're the farthest apart. All right, I did not keep that under 3 minutes, which was my goal, but I kept it under 5. Bye.